All right, okay. So this is the conservative form. And to really use finite difference, we need the integral form. Okay, so to get the integral form, we'll just take, this is the most convenient form. We'll take this and integrate over, actually, I'll just call it a spatial domain omega, right? And well, let me just call it omega I, because in reality, if I have a mesh, let's think of a spatial domain, I'm just going to divide it into multiple non-overlapping, but also basically a partition of unity, right? So that's the word people use. It can be triangle, it can be a quadrilateral, it can be any shape you want, really. And you can use a Voronoi diagram. Basically, anything that partitions the space into small volumes is fine. And you denote 1, 2, 3, whatever. You index the you index these volumes. So as basically, if you integrate over any one of these volume, the differential equation, the integral should still be equal to 0, right? Because point-wise, if the differential form is satisfied, then the integral form is also satisfied. That's what we want to make sure. If the integral form is satisfied, I'm not sure about the differential form, because the solution may be discontinuous, right? So in some sense, the integral form is in mathematics they call it weaker than the conservative form. Weaker means if a solution is a solution of the integral form, it does not have to be a solution of the conservative form. But if it's a solution of the conservative form, then it has to be a solution of the integral form, right? So it's a one-way. It's a necessary but insufficient condition. Okay, so this is weaker than conservative form. Okay, so now if you use divergence theorem on the spatial derivative, what does divergence theorem tell you? What's the integral of divergence over a space? It's a surface integral of the flux over the surface, yes. So this, first of all, I'll commute this ddt to out of this volume. Okay, well, I have dx, let me just write dx. So plus, now I have what I call partial omega I. So partial, so in mathematical terms, if I have a contiguous, if I have basically any set, the partial of this set means the boundary of this set. Okay, so any point, if you take any point and you take a small ball over this point, if the ball has to contain both points inside the set and outside the set, then this is part of the boundary, right? I mean, it makes sense, right? If you have a boundary, you take a small ball around, no matter how small the ball is around a boundary point, then the ball has to contain both points in and out of this set. Right, so this is the mathematical definition of the boundary. Then you have f w dot with the normal of the boundary. I'll just write ds equal to 0. So basically, the goal of this divergence theorem is to get rid of all spatial derivatives. And okay, so now this leads to finite volume in a very natural way. This is because this is just the let me just call VI the size of the cell. Some people also write just the it looks like the absolute value, but it's actually the area or volume of this volume I times times WI average, the average value in the cell, right? Okay. So now, what's the boundary integral? So if I have a cell, the boundary is this, right? Okay, so I have to somehow integrate over all the boundaries. And so in finite volume, the boundary of each cell can always be written as the summation over two parts. One part is the boundary between this cell and some neighboring cell. Right? So for example, in the blue cell I just highlighted, every part of the boundary is the boundary between this cell and the neighboring cell. But if I look at a different boundary, for example, if I look at the green boundary, only these two boundaries are between a cell and a neighboring cell. And then there is another part of the boundary, right, as black, to be the boundary of the entire volume, right? So basically there are two parts in this. One part is the summation over j in the neighbor of I, okay, and the integral is over I'll just call partial omega ij. So that's the surface that separates the cell I and cell j. Okay, the flux dot with n ds. And then there is also another term that is basically, there is no summation anymore. It's basically that I call partial I and exterior, right? So that's the boundary that separates the cell I, volume I, and the exterior of the domain. Equal to 0. So up to now, I still haven't made any approximation yet, right? So all the derivations are mathematically exact. It's mathematically exact, but I cannot actually use this directly in a computer, because why? Because, well, there is integral, and also I actually don't know the exact value of W on the boundaries. So I have to do some approximations. So in finite volume, these surface integrals are actually what I approximate. So I would approximate this surface integral as f of ij. So that's the flux between the cell I and the cell j. All right. It's actually this is approximate. This is usually written as fij times nij. So nij is like the average. So let me just write nij is equal to just this. Right. So basically the flux would be whatever this is divided by the nij. Right. So nij is the size of the surface element that separates the two volumes, and this integral is approximated as fi exterior times ni exterior. All right. So basically, the task of finite volume is to approximate the fluxes across different interfaces using only the information from the adjacent volume averages. All right, any questions? Yes?
Is it actually possible to interpolate the W's in the cells to the boundary and use the functional form of the flux to calculate the flux directly at the edge?
Right, so the question is it possible to interpolate the F's, the value of the W's into the boundaries, and then use the functional form of the flux to compute the integrals, right? So that's actually the most obvious thing to do, in some sense, right? So let's actually try that next. But before we go there, any other questions on this derivation? So this is basically the derivation of a general form of finite volume. No matter what kind of finite volume you do, it's actually exactly the same. Different ways of finite volume is just different ways of approximating these fluxes Fij and Fi exterior. Right, no questions?